And I'm sharing my screen. I hope that's all right.
Yeah, we can see it. I
All
guess,
right.
yeah. Okay, cool. I was just gonna say the cursor is on the front of the slides, but now it's not. Great. Yeah, so whenever you're ready, basically.
Yeah, thank you.
All
I'm
right,
very
great.
excited to be here. Sorry,
Oh
I
yeah.
cannot be there in person, but I'm going to be talking to you about rewards in multi-agent systems, and just to say a bit more about this. I think multi-agent systems actually offer a really interesting playground for reinforcement learning agents. Because these agents need rewards and an interesting life, basically, in order to learn and to develop interesting behaviors. And one way to obtain this is to have other agents in the environment and to interact with them and to use these agents both as a source of basically non-stationarity, but also as a source of reward. And so the talk that I'm going to give is basically trying to understand how we can leverage other agents in order to make these environments for RL. And I'm going to show you first a case study of a particular way of leveraging rewards from other agents, which is to use a gifting mechanism. This is mainly empirical work that was done in collaboration with my master's student, Andrei Lupu. And then I will talk a little bit about some theoretical ideas in reward design, where we've taken some initial steps, and there are actually lots of other opportunities, and maybe some of the people participating can get interested in this problem, and I'd be very glad to talk to them more about it. So gifting in multi-agent reinforcement learning is a mechanism that we've tried to explore a little bit for a common pool resource appropriation problem. So this is a problem where you have resources. These resources can renew and they're consumed by the agents. Whenever the agents consume these resources, they get rewards. But the resources only continue renewing if you have a minimal density that's maintained, and otherwise, things collapse. So you can think of this as, for example, if you're farming, if you're over farming, right, at some point the earth gets depleted and there's no more crops. And so if you have this kind of overconsumption, the pool of resources becomes depleted, and this leads to tragedy of the commons types of phenomena, where the agents, none of them can really do well anymore because no rewards are anymore available. And so the main idea that we try to explore here empirically is whether we can use sort of gifting mechanisms between the agents in order to entice them and encourage them to avoid this kind of overconsumption behavior. And so the idea is, rather than having sort of a centralized mechanism, individual agents can choose to give a positive reward to some other agent in order to incentivize them to do a desirable behavior, for example, not to consume too much. Now, why gifting? Because gifting is really very pervasive in human economy. Throughout history, if you wanted, the ruler of the kingdom to be nice to you, you would bring them some gifts. And even in animals, there's a certain hierarchy, and people who are lower in the hierarchy bring gifts to the ones that are higher in the hierarchy. And it's also very consistent with the core idea of reinforcement learning, which is that rewards are a driver of behavior. So you can think of these gifts essentially as integrated in the reward signal that's coming anyway from the environment. It's just that now this reward comes not from the environment itself, but from a different agent. And in some sense, if we could figure this out, it alleviates a little bit the burden of figuring out a perfect centralized reward mechanism. And maybe the agents can figure out how to improve the collective behavior or the learning speed by providing these rewards more frequently to each other. And so the dense reward signal can also help in terms of the learning speed. So this was sort of the motivation for this work. And now, of course, if you think about how to actually implement it, there's various choices for gifting mechanisms. And so we looked in particular at 3 different choices that seemed reasonable. The first one, which I'm going to call zero sum, means that an agent can choose a gifting action that just transfers a certain number of units of wealth or reward to another agent. And this means that, the target agent gets plus G, and the one that is giving the gift receives immediately minus G, right? So this is the sense in which it's zero sum. And you can now think of whether you want to sort of allow a finite budget or not, but this is sort of the basic idea of what happens on one gifting action. The fixed budget idea is in order to encourage agents to give without sort of perceiving this as an immediate problem. And so an agent might have a fixed budget, and every time that it gives a gift, this budget gets decremented. When there's no more budget, it can no more give any gifts. And the recipient receives immediately a reward of plus G, where G is the value of the gift. And then the third possibility is this replenishable budget idea, where we also have a budget, but it's really sort of a fraction of the actual real rewards that the agent receives. So initially there's no gifting budget, but if an agent gets a positive reward from the environment, some fraction of that reward goes into this budget, and the agent can choose later on to give some of that to another agent. And otherwise it's the same as the other ones. So, the reason why we thought about the fixed budget and replenishable budget was that we wanted to make sure that agents would not perceive gifting immediately as somehow a bad action that should be avoided, and therefore sort of never do it. Now, in order to actually understand what would happen if we introduce these mechanisms, we use this harvest domain that came from Julien Perolat and colleagues, where you have some apples. These are the green crosses in the picture. They're growing inside of a grid world environment. You have some agents. In this case, there are 10 agents that are the red triangles that can go around. And each of the agents gets a +1 reward whenever it eats an apple. But the apples only renew if there's a minimum density of other apples in their vicinity. And so if you eat a whole patch of apples, there will be no more apples that grow there. And these agents have, in the original implementation of the environment, a tagging beam. The tagging beam essentially is like a weapon that incapacitates agents in their neighborhood and prevents them from eating the apples. But we added to this a gifting beam, and the gifting beam just takes a +1 reward and spreads it around to the agents that are within range. And so if you have only one agent that's close to you, it will get the entire reward. But if you have a couple of agents that are close to you, then this reward is going to be split up among them. And this is all sort of deep RL in terms of the training of the agents. The agents have a first-person view of the environment. And so now we ran various experiments in order to see which of these strategies sort of prevent tragedy of the commons and what kinds of behaviors come out. And so the first curves that I'm going to show you are basically performance curves. These are the return per agent in the left graph and the sustainability in the right graph. Sustainability in this case means what is the average time between positive environment rewards that the agents are getting. So not the rewards that are coming from other agents, but actually eating apples. And in both of these cases, high is good, okay? And we are training all of these agents with DQN, which is very standard DeepRL algorithm with epsilon greedy exploration. And we compared the three different gifting mechanisms that I discussed, and also no gifting. So that's the default version of the environment that Julien Perolat had. The agents still have tagging actions in that version as well. And so the first thing that I want to say is that eventually all of the agents learn how to do this task. And so all of the curves end up roughly with the same performance. But you see this trough here in the middle. Okay, this is where the tragedy of the commons happens for all of the agents except the zero-sum agent. Okay, so they learn how to get rewards basically by eating apples, and then they're overeating. Okay, and the production of apples decreases, so they go through this trough where they cannot get rewards anymore, and then gradually they learn a reasonable policy But this agent that does the zero-sum gifting never goes through this drought and continues to sort of improve throughout. So that's kind of interesting. Now, another question is, could we have avoided the tragedy of the commons somehow anyway, or is the gifting really important in this respect? So in order to understand that, we actually took the models that we had trained, saved them at regular intervals, and then evaluated what happens without allowing anymore the choice of tagging and gifting actions, okay? Just allowing the agents to move around the environment and eat apples. And in this case, all of the agents do collapse into tragedy of the commons, which is what we would expect, because that is a natural equilibrium in this kind of problem. But the zero-sum gifting agents actually collapse slower. And that's basically because early on, they learn these policies that exhibit more restraint, and these policies take longer to sort of go away and revert to the Nash equilibrium. Now, another thing that we looked at is what kind of policies the agents learn in terms of tagging behavior and in terms of gifting behavior. So in terms of tagging, as the tragedy of the commons starts manifesting, which is the first vertical dotted line in this picture, all of the agents actually start tagging more, right? Because they're just trying to prevent the overconsumption. But the zero-sum gifting agents actually are pretty constant throughout. The only other interesting bit is that at the very beginning, they seem to tag a little bit more. Okay, and that's really because of the epsilon greedy exploration policy, and we think it's a side effect of that policy, in fact, rather than sort of a real phenomenon. They learn to tag because that means they're not going to gift too much and get too many negative rewards from the gifting. By the end, they are still actually tagging a lot less because there's not as much problematic behavior, right? And so they don't need to sort of exert this force. In terms of the gifting behavior eventually also goes away because by the end, you actually don't really have to disincentivize the other agents from consuming, okay? They just end up sort of occasionally tagging other agents, but generally speaking, being reasonable. And the agents that don't have a negative reward for gifting continue to give these gifts for longer. This is also reasonable because that nothing costs them, right? Whereas the agent that actually pays for the gifts is sort of stops to do that very early. In the paper, we also analyzed the equality among the agents, like are some agents, ending up being more starved than others, and actually all of the methods converge to roughly the same measures of equality according to the Gini index. So just to summarize, this sort of active reward sharing among agents can really mitigate unwanted equilibria, such as tragedy of the commons. There's, of course, other ways to achieve this goal. For example, one might think of setting up correlated equilibria, but maybe that's a bit harder to design, right? It's a more centralized approach, whereas gifting is a very local sort of per agent approach. It's also interesting to look at these behaviors and what happens, not just the performance, because sometimes there can be unintended sort of side effects of the strategies that we have, and it's interesting to see that. Now, this was purely empirical work, and it was in some sense heuristic, right? Inspired maybe by economics, but very much heuristic. One of the things that I'm quite interested in understanding is the ways in which we can formalize these notions of tasks and preferences that other agents might have and express them as rewards, maybe even compute the best rewards possible. So I'm going to show you now sort of a bit of the different flavor of work that talks about the reward design problem. Here we're going to take the perspective of just having two agents, okay? And this is really based on a paper that we published in NeurIPS last year. And while I'm going to give you the high level of overview, the technical details are in the paper. So here we have two agents. We have Alice, which is this white agent here, and we have Bob, which is this little robot. Bob is our usual reinforcement learning agent that acts in the world based on the state that it observes, and it gets rewards, and the rewards are provided by Alice. And really, Alice is going to compute this reward function based on some notion of task that she has in her head. And so a lot of what I'm going to talk about is what are reasonable notions of tasks, and under what circumstances can we compute an associated reward function that captures the nature of the task. And so there's different task types. The three that we discussed in the paper are the set of acceptable policies, policy ordering, and trajectory ordering. And I'm going to sort of tell you some examples and a bit of a definition in each of them. Initially, we thought that the nature of the task is going to make a big difference. It turned out not to make a big difference. So, but I still want to sort of convey all of these to you. So what's a set of acceptable policies? A set of acceptable policies just says, here are some policies that are better, right, considered better in the environment. So for example, if we have a little grid world navigation task, we might say reaching the goal in at most 10 steps in expectation is the set of acceptable policies, okay? And so you can think of this as a constraint on policy space where the good policies are all valued better than the bad policies. Policy ordering is something that essentially puts a partial order in policy space. So for example, we might say, I prefer that you reach the goal in 5 steps, but if we can't do that, it's okay if you reach it within 10 steps, and otherwise I don't really care. Okay, so that's a partial order in policy space. And then trajectory ordering talks about particular trajectories, perhaps in the environment. So for example, I might say, I prefer this agent to reach the goal and avoid the lava at all costs. Okay, so that says, you know, the dark blue trajectories here are preferable to the light blue trajectories. So these are examples of each of these task types. Now, what does it mean for a reward function to realize a notion of a task? In order to define that, we're going to consider an environment, which is a controlled Markov process. So this means it's just like an MDP, but doesn't have the reward function specified yet. But there are states, there are actions, there are Markovian transitions between the states conditioned on action, and it's all fully observable. The task is going to be one of the 3 types of tasks that we discussed. And we're going to say that a reward function realizes the task in the environment if the reward function leads to a value function, an associated long-term value function, that respects a set of inequalities. And so for the set of acceptable policies, what we want is the value associated with good policies to be superior to the value of bad policies. Okay, and here we have an initial state as 0, so we're comparing the values with respect to that initial state. But obviously this can be also done with initial state distributions. In policy ordering, we want the value functions to be ordered according to this policy ordering that's been specified. And in the case of trajectory orderings, we would like the returns along these trajectories to be ordered in the order pre-specified. So in this paper, we explored 2 questions. Okay, the first question is, when can a task be realized in a controlled Markov process? And so in other words, we wanted to know, given any task and any controlled Markov process environment, is there a Markov reward that realizes the task? And actually the answer to that is negative. Okay, and I'm going to show you one example, one case in which this is not really true. Okay, which is if you consider this little grid world, if you say something like, you know, I prefer policies that always go in the same direction. Okay, this is actually not expressible through a Markovian reward. Policy itself is Markovian, okay, because you can sort of specify the action, but we can't really express this because actually there is some non-Markovian information that's not part of the state, right? Which is what have I been doing prior to arriving here? And in order to sort of differentiate the value of these two specific policies, always go left and always go right, from the value of everything else, we would need that kind of information. Now, is this bothersome? From my point of view, it's not necessarily, because, one might think about it as there's a mismatch between the way that we've defined the state and these preferences, okay? The preferences are on policies, which are these sort of large objects that have a global view of the environment, whereas the state, the way that we've defined it, is too narrow. If we added something to the state, for example, if we remembered some history about past actions, this would not be a problem. I still think that it's an interesting question how to sort of decide whether the state information and the sort of task information are actually compatible with each other in general. And that may be sort of an open question for future work. Now, the second question is, imagine that I have an environment, I have a task. Can we actually, and imagine that a reward function exists, could we actually compute one, and can we compute it efficiently? Okay, so we want a procedure by which we can, Alice can ingest an environment and then take the task that she has in her head and output a reward function, or output, nil if this reward function does not exist. And interestingly, this problem can actually be solved in polynomial time for any finite environment and for any of the kinds of task descriptions that I have given you before. And the basic idea here is to use a linear programming approach, okay, and to set up a set of constraints that specify the task. And then it's pretty straightforward to show that this linear program either has no solution, for example, in the task that I've showed you before, or that it can compute a solution if one exists in polynomial time. And this is because the program itself is polynomial in the size of the environment. Now, these current results assume that the designer knows the environment and knows all the preferences in advance. Okay, and so this is a very big assumption, right? Basically, Alice needs to know everything about the environment that Bob is going to be in, including the transition probabilities. But it would be, I think, really interesting to think about an iterative approach. So you might imagine that Alice knows something about the environment and has some preferences, computes a reward function, observes what's happening with Bob, and then refines that reward function, right? And that this is an iterative process in which both Alice's computations on the reward and Bob's sort of computations of its policy and value functions kind of happen at the same time. That would be much more like a sort of dynamic multi-agent game kind of scenario. Another interesting question here is what happens if Alice and Bob actually do not have the same features? So here we've assumed that they both know the state space is fully observable. But really, if we think about the deep RL setting, right, Bob might be an agent that is learning something and is learning some features, and maybe Alice has completely different features because maybe Alice is an expert in this environment. I'm not sure if anything interesting can be said in that case, but it seems like from a practical point of view, an interesting setting. And then finally, sort of going back and linking to the gifting work, what happens if we have more than one designer? So here we had Alice, but maybe there are several sort of different agents that have tasks in their heads, all about the same environment. Under what circumstances can we come up with some way of sort of generating a reward function for Bob in an interesting way that still provides some guarantees? So these are all open questions. We've barely scratched the surface, I think, with this paper, and I'd be interested in chatting further. And so I will stop there and happy to take any questions.
Awesome, thanks a lot. That was, I think, some really interesting work. Yeah, it looks like we have a few questions. I'll go to Kostas first.
Hi, thank you. Very interesting work. I wanted to ask you about you claimed the polynomial time algorithm for a given task and a given environment. I wanted to understand how you specify the task in the input, like what's the description complexity of that?
Yeah, so the task is specified in this case by imposing these inequalities in terms of the value function space. And so, so basically what are these linear programs that we work with? The values, okay, the value functions have to be in this sort of relationship. The value functions have to be value functions, so they have to satisfy Bellman equations, right? That's a different sort of set of constraints. And then the third ingredient here is what I'm going to call sort of fringe policies. So if you consider, for example, in the set of acceptable policies, all the policies that are good, and then you consider all the policies that are one action different from the good policies, okay, it turns out that the only constraints that we really need are between the good policies and these fringe policies. We don't need to care about anything else. And so that's the set of value function constraints that ends up in this linear program.
So just to be clear, you would list all the good policies and then say, you know, these have to, like, you provide a list of all the good policies and say these have to dominate every other policy? Is that the...
They have to dominate every fringe policy, and that's sufficient for them to also dominate all the other policies.
Gotcha. So the former is the clever way you do it, but the constraint you want is that a list of policies dominates all other policies, correct?
Yeah, that's correct, except we can very heavily prune this set of constraints by using this notion of a fringe.
And in the policy ordering, you similarly will give a list of policies and how they order.
So the policy ordering turns out to be extremely similar because really we just have a set of these inequalities of value functions. Now, obviously, if you had, so the set of acceptable policies is in some sense easier to reason about. And initially we thought that it would be quite a bit easier actually than either policy ordering or trajectory ordering, but it turns out that in the end, we still end up with linear programs by sort of very similar reasoning in these other cases as well. And so complexity doesn't really end up being that different. Now, I want to say a couple of other things. So first of all, in terms of the set of acceptable policies, we could have partial specifications in this case, right? So partial specification might say, you know, I don't care what you do, except at this state, I prefer that you go up instead of going any other direction, right? So in this case, we can, you know, we can further perhaps be clever about how we enumerate these constraints. And secondarily, we have looked into approximate notions. So, you know, you have to be, you're going to be better by at least a certain amount, right? So sort of like a margin, and that also doesn't end up really being fundamentally much different. Although empirically, you know, if we have this kind of margin, it makes it a bit easier to solve these problems in particular environments.
Well, thank you. Who else wanted to ask?
Hi, thank you. With regards to the gifting work, like it seems to me that the zero-sum approach actually is the only one that considerably does better than the no gifting approach. But to me, it also seems the hardest one for the agents to learn. So why is the zero-sum approach so much more successful? Like, is it like an intuitive explanation you can give, or?
Yeah, so, you know, I also agree that, and our intuition was that it's going to be hard to learn because you have these immediate negative rewards. But so my sense is that actually it's a combination of the specifics of this environment and, you know, having, for example, the tagging action versus having the gifting action and the way that we do the exploration all matter. And in this case, the agents, you know, don't seem to care that much about the immediate negative rewards that they get from the gifting. And they don't they don't select the gifting action too much, so they don't become depressed about those actions either. I don't know if this would always translate into other environments as well. So I have the feeling that it's also a bit specific to this particular kind of environment. But I was honestly quite encouraged because it's the one that would make most sense, right? Even if it's the hardest to learn. I suppose that there may be other ways of maybe setting up, for example, the replenishable budget, right, in a way that would make it better, but we never got to explore that.
Yeah, because if I remember correctly, the original work from Perolat, it's all the official final policy that did not have the tragedy of the commons was where they each tagged each other often enough so that there were less agents in the environment, so they basically could not eat all the apples physically because they didn't have time enough. So maybe here also the zero-sum ones, like you showed in the follow-up slide, they tagged each other less as well. So maybe that's also a reason why it fares better in this specific environment. So it might be interesting to look at other ones.
They end up tagging each other less, but they also, eventually, like if you let them go all the way to the end of learning, they do end up with essentially a very similar policy as everybody else. So they do tag more than they use gifting towards the end.
Yeah, maybe the cleanup environment would be interesting next. Thank you.
Agreed.
Let's see, were there any more questions? I guess I just had one very basic one. So I just wanted to double check. So for the linear programming approach you were talking about, is this just based on optimizing over occupancy measures?
Yes, indeed. So
Okay,
the
cool,
value
cool.
function is estimated based on the occupancy measure.
Yeah, that makes sense. Okay, cool. Thanks. All right, great. Maybe we should stop there. So I think we'll have a quick break until 3:30, and then we'll come back for the last talks of the day. And let's thank Doina again. That was great.
Thank you very much.
Thanks a lot.